Hello everyone and welcome back. So today we're going to be in Chapter 4, Equilibrium of Coplanar Force Systems. Now you're like, well, we did coplanar forces last time, so yes, but now they're in equilibrium. Last time we didn't really care, we just said, okay, we got a bunch of forces, add them together, even if those forces would be pushing our thing and causing it to fall. No, now everything is going to be held stationary, it's in equilibrium. So what does this mean? Well, it's when the resultant of a force system is zero. So we add all the forces together, and our resultant force is nada. It's zero. So for a force system to be in equilibrium, the algebraic sum of all forces along any axis in any direction must be equal to zero. So if we have a bunch of force vectors, they should end up back where they started if we add them all together. So the resultant force would be zero. Or if we're looking at all the components, well then all the x components, or y components, would add up to be zero. Lots of ways to look at it. Also we have to worry about is the moments, because just because it's not going to translate doesn't mean that what you're doing isn't going to cause it to rotate. You have to make sure that there's something to keep it from having that happen. So all the moments, or that tendency to rotate, must be zero as well. Now, how do we figure this out? Well, to do that, we're going to have to learn how to draw a free body diagram. That's the biggest and most important detail from today, a free body diagram. So what does it look like? Well, it looks like this. We have this fairly realistic drawing, and we want to translate it into a less realistic, but much easier to understand free body diagram. Now, how did we do that? Well, there's various steps. First off, we want to isolate the body from all the other bodies. So in this particular case, I want to look at the point that needs to be in equilibrium. Technically, I can go anywhere. I can go right here. I can go right here. Any part of the system should be in equilibrium, but only one part kind of connects all the forces together in a real easy to understand way. And that's right here, right at the center. So if you see a bunch of things intersecting, that's probably a good place to have a free body diagram. Now that's more or less a point. We're going to say that it doesn't have any size. And so we cut the ropes, cha-cha-cha. And when you do that, whatever you cut, it turns into a force. You just draw an arrow going towards what you cut. That's what we have right here. Now you have to show all the forces that are acting on this body. In this case, I cut everything. It was pretty easy. But let's say that I had an object. Okay, it's sitting on a surface, and it's got a force or two applied to it. Well, then I kind of cut away the floor. Okay, I do that. And I say like, okay, well now there's a force pushing up on it because the floor is not there anymore. That's good. But you're missing one force. That would be its weight. You have to remember that it also has a weight. So sometimes you'll have to take that into account too. Be very careful to show it. And also be very careful about the line of action and the magnitude if you can. Like you don't have to draw these arrows to scale, but it will really help if you're at least trying to point them in the right direction. Finally, indicate any unknown forces with a symbol. You don't have to have a number. You can just say, okay, this is going to be force 1 because I don't know what it is. Then I have an angle here because I don't know what the angle is either. And that will help you have an idea of how many unknowns you have to see if you can actually solve it with the number of equations that you have. So we got a little bit more time, so let's go over supports. So there are lots of things you're going to see in these various problems. And each of those are going to have their own way of drawing it when you turn it into a free body diagram. Like I said before, we have a rope right here. When we cut that rope, it turns into a tension, which is just a force pointing towards where you cut it. Or it might have a roller, which can only give me a force in the upward direction, which is directly perpendicular to the surface that the roller is laying on. So you see right here, it's pressing up on it. Right here, it's once again pressing up just away from this surface. And I might have a smooth surface. If it's smooth, that means that there's only going to be a normal force pressing up on it. Later on, we'll hit on friction. So when we get to friction, well, then you'll have to include that as well, which will look like that. But we'll get to that later. Don't worry about it for now. And you might have a pinned or hinged roller, which is right here. That keeps it from moving either in this direction or this direction, just like your door. If you pull on your door to open it, it will rotate around the axis. If you pull your door that way, like you're trying to pull it off of this axis, it doesn't go anywhere, it's stuck. And then finally, a fixed one. Think diving board, okay? The diving board, when you're stepping on it from the edge, it is completely stationary right there at the wall. It doesn't move. It doesn't move up, down, sideways, and it doesn't rotate at the wall. Like it bends, but the diving board doesn't suddenly just flop off and rotate. If it does, it's a pretty terrible diving board. Now, I do expect you to memorize these eventually, to understand what forces you're going to have. Now, I'm not saying memorize as in you're not going to have references. It's just you're going to save yourself a lot of time if you know what's going on here. If you know how to find these forces. So please, please, please work hard and try them out. Make sure that you are memorizing these, or at least trying to. And also just mark it in your book. Put a little tab in this section of your book so you can find it later if you need to. So that'll be it for this time. Thank you so very much for listening. I'll see you all later. Bye-bye.